Welcome back to my GIS YouTube tutorial. With me again, Godfrey.Chaula. Today, we are performing annual land surface temperature for Lilongwe City. You can choose an area you want. We'll be using Landsat 9 satellite imagery, processed directly in Google Earth Engine. By the end of this, you'll have a clear representative thermal map for the entire year of 2023. Firstly, let's define our study area. We'll import our Lilongwe City boundary, and using the Map Center Object function, we'll center our view right on the city. This boundary is super important. It acts as a spatial constraint for all our subsequent calculations, ensuring we're only analyzing data within the city's jurisdiction. The next step that we are going to do is doing cloud masking. You know, remote sensing data is often contaminated by clouds and cirrus artifacts. If we leave those in, they'll definitely ruin our thermal analysis. So, we define a mask function that looks specifically at the QA pixel band. By applying a bitwise operation, we filter out cloud shadow, and cirrus pixels. It essentially cleans our raw data before we start the heavy lifting. So here, everything will be clear. After done with the cloud masking, we are going to load our Landsat 9 image. Alright, now we call our image collection the Landsat 9 Collection 2, Level 2 dataset. We chose Level 2 because it's already atmospherically corrected, which is essential for accurate surface temperature readings. We'll filter this collection for the entire 2023 calendar year and map our masking function over the entire set to make sure every single image is clear and ready for processing. Now, let's dive into the core, the get LST function. This is where the physics happens. First, we apply scaling factors to convert the raw digital numbers from the satellite sensor into actual physical units for surface reflectance and thermal breadth. Second, we calculate the Normalized Difference Vegetation Index, or NDVI. We need this because healthy vegetation reflects energy differently than bare soil or concrete. Third, we use that NDVI to estimate the surface emissivity. Everything on Earth emits thermal energy differently based on its material properties. By calculating emissivity, we correct our thermal readings to ensure the final result reflects the true surface temperature. Finally, We use the inverse of Planck's law to convert these corrected brightness values into degrees Celsius. With our algorithm ready, we'll map it across the entire year of 2023. We then apply the median reducer. Why the median? Because it's robust against outliers. It ignores those anomalous cold or hot readings from a single bad pixel and gives us a stable, clean, and representative average temperature for the year. Finally, we'll clip the data to our Lilongwe City boundary for a clean presentation. For the final layer, we'll apply a visualization palette. We use green for cooler areas, like water bodies or dense parklands, and shift to red for the intense heat zones of the built-up urban center. Finally, we run a reduce region function to print the mean annual temperature for the city to the console. This gives us the hard, quantitative number ready to read in Google Earth Engine.